Welcome, I'm Jane Waterhouse from Tropwater at James Cook University, and I'm just going to give an overview of our component of the inshore water quality monitoring in the marine monitoring program. So I'm just going to share my screen so we can look at some slides together. So I'm part of a largish team, so I work alongside Stephen Lewis, Caroline Pettis, Dita Tracy, Jane Mellors, Cassandra James, and then in Cape York, Christina Howley from Howley Environmental Consulting works with us. We're also in partnership with the Australian Institute of Marine Science, who deliver part of this component too. So to put the marine monitoring program into context, it's a critical part of the broader Paddock to Reef integrated monitoring, modelling and reporting program. That program in turn supports the main reef water quality policy for the Great Barrier Reef, and that is the Reef 2050 Water Quality Improvement Plan. So it evaluates the outcomes and progress of the actions included in that plan. So here in the diagram, you see the main components. So there's activities going on in the paddock, in the catchment, and then here's our part, the marine monitoring program, which has seagrass monitoring, water quality monitoring, coral monitoring, and then e-reefs marine modelling. So since 2005, the program's been assessing the condition and trends in ecosystem health and resilience indicators for coral and seagrass in the inshore Great Barrier Reef. So we've been doing this for a little while. So where do we monitor water quality? So as I said, it's done in conjunction with the Australian Institute of Marine Science and Howley Environmental Consulting. Most of our sites, as you can see here, are located in the open coastal water body. We've got routine water quality sampling at 58 stations. Each of those sites is visited between 3 and 12 times a year. And then we've got additional event-based sampling in the blue dots here, and that's done at 26 stations, depending on where the event occurs. That's only occurs during periods of high flow, and we get also these routine sites when we're collecting in a particular region. In addition to those, it's continuous logging of water quality at 16 stations. So these are highlighted by this symbol, and there is at least a couple in each of the main regions. So what do we measure in the inshore water quality program and why? So a number of physical variables, so temperature, salinity, and water clarity. So they tell us about the movement of water and the freshwater influence in coastal waters, as well as just those general environmental parameters, including salinity. Our biological variables, so chlorophyll, it's a pigment found in phytoplankton and also total suspended solids. So that's an indicator of turbidity, that's the cloudiness of the water. That's a fairly extreme example of very turbid waters. So that tells us about productivity and light availability, which is really important for coral and seagrass health. Our chemical variables are dissolved nutrients, particulate nitrogen and phosphorus, dissolved and particulate organic carbon, and coloured dissolved organic matter. So they tell us about nutrient concentrations in a bit more detail, and we use that data to validate the satellite imagery, which I'll talk about in a minute. So in terms of the satellite products, so Caroline Pettis and our team leads that, and she combines MODIS and Sentinel satellite imagery with some of the wet season water quality data and the environmental data to generate a few products or answer a few questions. So we're assessing the extent of river flood plumes during high flow conditions. How far does it go? We're characterising different types of water in the reefs and understanding those general water quality characteristics and the gradients as we move from the coastal areas further offshore. We are identifying where the average long-term concentrations of suspended sediments, chlorophyll, particulate nutrients are likely to be above the wet season guideline values by combining those data sets, and also assessing the exposure of coral reefs and seagrass to potential risk from land source pollutants. So it's really telling us about the wet season conditions at multiple scales, both temporally, so daily, weekly, seasonally, annually, multi-annually, as well as the water composition over very large spatial areas. So just a little bit more about that method so you can understand how we get from an image to a colour class. So the images, true colour imagery can be divided into a number of colour classifications that relate to different characteristics. So here we show these brownish waters are characteristic of higher turbidity, and here's an example here of these colour classes in the satellite image here. These 5 and 6 are more these greenish waters. They're characterised by more nutrient enrichment. And then colour class 6 colour class 6 here is a bit more on the edge of the plume, and then we have this sort of offshore water body where you return to a condition with limited influence of, or no influence of, land-based runoff. So here's an example of how that image has been interpreted into those 6 colour classes, and from those they're combined to be assessed as the full plume extent. In terms of understanding what the water quality characteristics are like in there, so say we take a water sample here and look at the concentration, we can say, well, in these primary, in these colour class 1, these are the sorts of concentrations of suspended sediment that we're seeing, and that's done at thousands of locations across the Great Barrier Reef to come up with this overall characterisation. So here we see an example, so that these 4 colour classes are classified into what we call primary. And here with total suspended sediments, you can see on a log scale, but that the concentrations in this primary water body, so this sort of stuff, is much higher, and it gradually decreases as you go from those secondary and then the tertiary water bodies or water types. Same for chlorophyll, and similar story for light as well. So we do see those gradients as you move outside the plume and transition back to marine waters. Just a little bit more about those wet season water types. So the primary water type, it's got high nutrient and phytoplankton concentrations typically, but typically highly enriched in sediment, and that's where it gets that brownish colour. Largely nearshore, inshore waters, influenced then by resuspension and river discharge. It's hard to tease the two out. The secondary water type is really the bluish green waters. It's typical of coastal waters where you've got algae, so often the sediment has dropped out, but you will still have some fine sediment there. Relatively high nutrient availability in those waters. You have more light because that sediment's dropped out, and it's typical in the open coastal waters, but also the mid-water areas, mid-shelf areas. The tertiary water type, our third water type, is our transitional area, sort of out of the plume and back into open marine waters. Typically still see concentrations of suspended sediment and neutral chlorophyll above guideline values in some instances. So it's not completely back to ambient, and we see that much further offshore, usually in the mid-shelf and offshore areas. So it gives you an idea of how we can try to characterise water quality across very large areas at fine time scales. So there are our methods. Let's talk about some results for 2019 and 20 and the pressures and drivers that influence those. So in terms of cyclone activity, it was very limited in 2019-20. There was only Tropical Cyclone Gretel, which really didn't do much. It was a fairly weak system. We see that reflected too in the wet season rainfall. So this figure shows the difference between the catchment average daily rainfall and the difference to what, so this year compared to a long-term average. You can see for this year, every basin was below the long-term average. It was all drier than the previous year. In particular, we saw the wet tropics basins having the below average rainfall, much lower than anything we've seen since the commencement of the marine monitoring program. Discharge tells a similar story linked to rainfall. So here we have the total Great Barrier Reef discharge. Along here we have the water years and the dates for each wet season, in a sense, we call it. So here our key is anything more than 3 times the long-term median is red, 2 to 3 is orange, 1.5 to 2 times the long-term median is yellow, and less than 1.5 is in this greenish colour. So you can see for 2019-20, we were below the long-term median discharge. And then here we can illustrate that by region. So if you have a look across here again, total discharge, the years, and then for each region, the same colour coding and the long-term average, we can see that every region was below the long-term median discharge for 2019-20. For the wet tropics, you can see it was substantially below and the lowest that we've seen for quite some time. Some of the basins in the Fitzroy region were slightly above the long-term median, but these are relatively small catchments like Waterpark Creek and Shoalwater. So as a result of that, there weren't any significant rainfall events and event monitoring wasn't undertaken in this season. We did generate remote sensing products though, so I'll show you those. This is an action-packed slide. So water type frequency is one of our main products. We've got on the left here a long-term comparison. So all of our data since 2002, the average conditions of that. Here is what we're calling a coral recovery period. We understood that we had coral recovery in that time. So they're the sort of conditions that I guess we would like to see. In the wet, these are the wettest years in that period, the driest years, and then here's the year that we're currently working on. At this scale, it's quite difficult to see the significant differences with each of these scenarios. The main message is though it was fairly close to the long-term average. There were some areas though around Cape York, the Fitzroy and the Burnett Mary region where we saw some extended areas of the secondary and tertiary water type in particular, and I'll explain that in a second. And these graphs off to the right give you an idea of, well, if you look at a specific location and the transect represented by these arrows for the Tully, Burdekin and the Pioneer, you can see how it fares compared to other locations. Here is the frequency. This is the distance along out from the coast. And in this example, you can see that here our 2020 year was fairly average, similar to the dry characteristic. For the Burdekin, a little bit different, but similar story there. And for the Pioneer, again, we're similar to the some of the drier periods represented. I'll just explain a little bit more about why we think we're seeing those extended secondary areas. So typically you'd see more of that water type extending further offshore if you've got quite large wet years. Here, this map is an example showing the difference between the long-term average and whether it was larger or smaller. So the red is where it was a greater area above the long-term area average, and then this green is if it was smaller. So as I said before, we saw some anomalous areas up around Cape York, Fitzroy and the Burnett Mary region. So particularly here with the secondary and down here, and even greater areas with the tertiary water type. So why? Sun glint can be a factor, the quality of the images, resuspension of marine in the marine environment from wind and wave is also a factor driving turbidity. So we might see that if we had more conditions where it was windy but also clear, so cloud cover can be a factor if you've got less rainfall. That can also lead to more algal growth. You've got more light, although we haven't really documented that evidence in the past. It could also be linked to having more discrete events and with the less rainfall then sort of hanging around for longer. The tertiary areas, the extension of those, we're not entirely sure either. Further investigation of those is required, and we're constantly learning in this program, but it could be driven by temperature or outer shelf nutrient upwelling, for example. So something that we need to look into. Surface exposure mapping is a tool that we use that assesses the likelihood and magnitude of the influence of each of those water types. So It looks at how much the water body or the water characteristics exceed the guideline value, and therefore using the frequency maps, the likelihood of exposure with those. So we have a simple exposure matrix where 1 is the lowest, so these greenish areas, through to red, which is the highest. We've got the same comparisons here in terms of the long-term average, a coral recovery period, the wettest, the driest, and the current year. We've also got a difference map. So where it's greenish, it shows we had a reduction in exposure. Where it's pinkish, it's an increase in exposure. So you can see, again, those anomalous areas around the further areas offshore in the Fitzroy, Burnett Mary and Cape York. But generally, it was a fairly low year in terms of surface exposure, which is exactly what you would expect with a low discharge. Just to show, illustrate where the different exposure categories are occurring though in terms of water bodies. So here, remember again, this is the highest exposure. Majority of that or all of that occurs in the inshore water body. We also see a similar pattern with the next category, which is the second highest. And then as you get further offshore, you start to see a larger proportion of that, the lowest exposure category. We also have river-derived dispersal. So it's a relative measure of loading, if you like, derived from the Reefs model. So it disperses an end of catchment load in the marine environment. So this is done for dissolved inorganic nitrogen, total suspended solids and particulate nitrogen. Here's an example here of the dissolved inorganic nitrogen output. So we show the result for the current year. We also have a pre-development estimate based on pre-development estimates from the source catchment models of the end of catchment loads. And then we have a difference map, which is what we're calling the anthropogenic loading map, because it shows what you would, I guess it takes out that natural influence that you'd see from the pre-development conditions. So these are useful to see on an annual basis, but we've also got this time series here, just highlighting that you can really pull out those wetter years and equally the drier years. Here's some big examples, 2019, 2011. So it's a useful way to look at how end of catchment loads are being dispersed in the marine environment. We also generate weekly outputs for each region, so taking into account factors that influence river runoff and marine conditions. So river discharge, wind speed, and then here's the water type maps. Here's an example here just to illustrate we had that rainfall event, and you can see that coming out in the river plume there. So if you want to look into more detail weekly, that's done for each region. So overall, our conclusions. So the 2019-2020 wet season was a relatively dry year. As a result, we had a constrained wet season influence on water quality in the Great Barrier Reef, and it was similar to or below long-term average conditions. That was reflected, those situations, in the water quality response. So it was generally good or moderate in most regions in 2020, as Renee had illustrated. And then just a really important point there, that remote sensing continues to be an important tool for assessing water quality at a range of scales. And I think there's real capacity there to look at it at finer scale as well. So you can find out more about the Marine Monitoring Program on the Great Barrier Reef Marine Park Authority's website. Also visit the e-Atlas. There's a page for each one of the program components there. And I'd just like to finish off by thanking our partners. So this is a collaboration between the Great Barrier Reef Marine Park Authority, the Australian Institute of Marine Science, ourselves, and the Cape York Water Monitoring Partnership. Our team, which I've already mentioned, our field support, Mission Beach Charters and Aussie Barra Charters, the whole Cape York team, the Australian Government for funding, the Bureau of Meteorology for the imagery, and then the Department of Environmental Science for the end of catchment loads data. So we work with a large collaborative team. So thank you for joining my talk today, and I'd be happy if you would like to follow up with any questions.